Okay, so in this example problem, we're going to be looking at Newton's law of viscosity and how it applies to a block of mass m as it slides down an inclined plane of angle theta over an oil slick of thickness d. And the objective is to determine a governing differential equation that describes the motion of this block of mass m as it slides down this inclined plane. And then from that governing differential equation, we're going to determine a velocity function for the block of mass m. So to begin, let's go through some of our fundamental assumptions. One, we're going to be assuming that the oil slick is a Newtonian fluid, so we can use Newton's law of viscosity. Two, we're going to assume that the velocity profile that develops in that oil slick is both incompressible and laminar. We're going to assume that the mass starts from rest. We're going to assume that we're neglecting aerodynamic drag, so no pressure drag, no shear drag on this block. And we're going to assume that the oil slick thickness d is thin enough or small enough such that we could assume that the velocity profile that forms in that oil slick is approximately linear. So the small gap width assumption, basically, where when that gap width is very, very small, you can approximate the velocity profile as linear. Okay, so let's begin by looking at a free body diagram of the mass m. Okay, so now we have our free body diagram of our mass m right here. There are a few forces acting on it. It's relatively simple because we are neglecting aerodynamic drag, but let's review some of those forces. So in the y direction, remembering that our local coordinate axes are defined as shown here. So our x-axis is shown coaxial with the inclined plane, and our y-axis is orthogonal to that direction. So that's why we have this inclined free body diagram, where again, we should draw that out. We'll have that is positive y, and that is positive x. Remember, your axes don't have to be perpendicular 90 degrees to the page like this at all times. They could be at any angle you want. And in Cartesian coordinates, as long as x and y are orthogonal to each other, it doesn't really matter how you rotate those orthogonal axes in space. So with that being said, let's go over some of the forces on this diagram. So first we have our normal force, which is the force of the oil slick acting up on the block. We have the y component of the weight of the block. We have our x component of the weight of the block, and we have our fluid shear force, which is opposing motion. So to begin, let's look at our Newton's second law in the x direction specifically. So we have some of the forces in x. We have that this is positive, and we'll have Wx minus Fs is equal to max. Now we have to figure out how to break down these two terms right here. So to break down the weight of the block, we're going to have to do some basic vector math. So we'll begin by drawing the weight as it actually is in the problem, because remember, gravity is directly downwards. So this is our weight vector. This is our x-axis. This is our y-axis. So if we decompose this weight along those axes, kind of like this, just like that, then we'll have this is the weight in the y, and this is the weight in the x. At this point, if you project out this a little bit more and then kind of connect it to the weight, you'll just notice that this right here is theta, which means that this is 90 degrees minus theta. So what we can say then is cosine of 90 degrees minus theta is equal to Wx over W, or Wx is equal to cosine of 90 degrees minus theta times W. And if you remember your trig identities, you'll remember that the cosine of 90 degrees minus theta is just the sine of theta. So now we have Wx is equal to sine theta W. Okay, so that's our first force that we needed to look at, this one right here. So the next thing we need to look at is Fs. Fs is a little bit more complicated, so let's draw that out. Here you could almost visualize if you look at maybe the block when it's right here. right? You visualize the velocity profile that forms in that oil slick beneath the block as it's moving downwards in positive x. You could almost visualize that it's going to look something like this, where this is our velocity, u, and then it decreases as you go down towards the ramp, and it is 0 at contact with the ramp because of the no slip condition. So if you draw that out in kind of a breakout diagram, which I have right here, you can see that, as we mentioned, our velocity is 0 at the inclined plane, so this is the plane, and the velocity is big U at the contact point with the block because of the no slip condition as well. So we have the velocity at this top profile is big U, and the velocity at this bottom profile is 0. So you have to imagine that the velocity of the block is increasing over time. The block is accelerating over time. So the velocity of the block, big U, is a function of time, a positive function in time. Therefore, the velocity profile in the fluid beneath the block as it moves down the plane is also a function of time. So we're kind of defining big U, as we mentioned, to be the velocity of the block, and little u is defined as the velocity profile of the fluid beneath the block as the block is moving. So you can kind of visualize that the velocity profile within the oil slick, little u, is changing pretty radically over time because the velocity of the block that is on top of it is changing pretty radically over time. So you can almost imagine that at very small times, so maybe right after t equals 0, the velocity profile in the fluid kind of looks something like this, right? The max velocity is very small, and that's because this max velocity is just big U, and big U at small time is very small. So then you can kind of imagine that as t goes to infinity, as a lot of time has passed and the block has had a bunch of time to accelerate and pick up speed, the velocity profile maybe looks something like this. And remember, this is little u right here, where the max velocity in the fluid profile now is very large because big U is very large because the block has had a ton of time to accelerate. So basically, at any given time, t, Newton's law of viscosity will apply. The velocity of the block big U is a smooth function of time. And so the velocity profile of the fluid beneath the block, little u, will also be a smooth function of time, and therefore the shear stress will be a smooth function of time. And so Newton's law of viscosity applies at every single snapshot in time of that velocity profile as it evolves beneath the moving block. So to write a more general form of Newton's law of viscosity that kind of produces that result that we're describing is we would say Newton's law of viscosity in this case could be written as tau of yx is equal to mu partial derivative of little u with respect to y. And that will maintain our time dependence in a way that is consistent with this problem. Okay, so now we're going to write out Newton's law of viscosity as consistent with what we just outlined. So tau of yx is equal to mu, which is the viscosity of the oil slick or the fluid, times the partial derivative of little u with respect to y. Now, what is little u? Well, we've established that little u is a function of time because big U is a function of time, and little u is just the velocity profile of the fluid beneath the block at any given instant, adherent to this diagram right here. So we could see that our velocity in little u varies from 0 at the inclined plane to big U at the block. So we're changing our velocity, a magnitude big U, over a distance d. So that's the slope of our velocity curve, of our velocity function. And then we just multiply that by y. So why does that work? So big U over d times y. You could see that at y equals 0, this function is 0, as it should be, because y is in this direction. So at y equals 0, our velocity little u is 0. So at y equals 0, this whole thing is 0, and little u is 0. Now at y equals d, so we go across this gap width, remember, this is d. As we go across this gap width, y equals d, d cancels, and our velocity is big U. And we've already assumed that we're assuming a linear little u, a linear fluid velocity profile. And therefore, this is a straight line from 0 to big U, which is exactly what we've outlined. So this is the velocity profile little u. Now, remember that big U is a function of time. And so this is the more precise form of the velocity profile within the fluid beneath the block at any given moment in the block's motion. Okay, so now we have our expression for little u. So now all we have to do is turn that velocity profile into a shear stress. So we know that from Newton's law of viscosity, tau yx equals mu du dy, partial derivative of u with respect to y, which is equal to mu. The partial derivative of this velocity profile with respect to y is simply big U of t over d. Okay, so that is our shear stress within the fluid at any given moment. Now what we can write is Fs is equal to tau yx times A, where A is the area of contact between the block and the fluid beneath the block. And we've already kind of described that here as A. So remember, shear stress is in units of newtons per meter squared. So you need to multiply by an area to get a force. So with that, we can write out our final force balance. So Wx minus Fs is equal to sine of theta W minus tau yx A, which is equal to sine of theta W minus mu u over d. We'll drop the function notation for now. It's just going to be implied times A. Okay, and that is equal to MAX. Okay, so now we just remember that the acceleration of the block in the x direction is just the time rate of change of the block's velocity. So we get equal to m du dt. Okay, cool. So our almost final expression is m du dt equals sine theta mg, right? We'll just break down our weight into mass times the magnitude of acceleration due to gravity, minus mu u over d a, divide out by m, and we'll now express this differential equation in first order linear differential equation form, which kind of gives us the perspective we need to implement our theoretical solution methods. So we write this as du dt, and we bring this over to the other side. So we have plus mu a over m d u equals sine theta g. Okay, so this is our final differential equation for the velocity of the block big U of mass m as it moves down an inclined plane of angle theta over an oil slick of thickness d and viscosity mu. Okay, so this is our final equation. You could solve this equation through multiple means. You can solve this by collapsing some of these constants into class constants, so to speak, and then solving it using separation of variables. You can solve it using integration factors. You could solve it through Python or MATLAB or Octave or any one of those scripting languages. For this video, what we're going to do is we're just going to jump to the solution, and then I'll make another video on how to theoretically solve an equation like this through both class constants and separation of variables and through integration factors. But for now, we're just going to skip to the solution of this differential equation so we can get to the final form and kind of examine theoretically what some of those terms represent. Okay, so this is the final form of our differential equation, which again, you can solve through separation of variables and class constants. You can solve through integration factors. You can solve numerically in Python or MATLAB, etc. But this is the final result. I got this particular solution through integration factors, and again, I will create another video that kind of walks through that derivation and that process. Now, one of the final things to say about this equation is we can kind of look at it and see what the governing mechanics are, and that kind of gives us some physical intuition into how the system actually behaves at a fundamental, essential physical level. So you could see here that at t equals 0, the entire system is at rest, because when t is 0, this is e to the 0. E to the 0 is 1, 1 minus 1 is 0, so big U is 0. So the block starts from rest as it should. At t equals infinity, this term is 0, so this term, this difference, is maximized at 1. So at infinite time, at steady state in other words, the system has reached its maximal or terminal velocity, which is just equal to sine theta g times md over mu a. So you can kind of see that the steady state speed, or the steady state velocity, is indeed just this term right here. And we can kind of examine that as the mass of our block increases, as the thickness of the oil slick increases, as the magnitude of gravitational acceleration increases, and as the sine of our angle increases, the steady state velocity of our block increases. Now, as the viscosity of the oil beneath the block increases, and as the contact area that the block has with the oil beneath the block increases, the steady state speed decreases. So a designer might derive an equation like this and then look at these factors kind of like we just did, and then say, okay, based on these factors, I know which factors are important in my design, which factors are not important in my design, and I can start to spec out the oil, the angle, the mass, the thickness of the oil slick, etc. You usually don't have much control over G, but that may change in the coming decades. Okay, and that should be it for this video. I really appreciate you watching. Thank you, and I will see you next time.